Hi friends, welcome to our YouTube channel Bright Education Center. Today in this video we are going to discuss the topics mechanical properties of bulk matter, that is solids and fluids. It's a chapter prescribed in the syllabus grade 11th CBSE syllabus. In this chapter we study about the properties of solids when we apply an external force on it. So how do these solids will behave when we apply an external force on it? That's the discussion point of this chapter. So mainly the nature of the solids, metals, some are ductile, some are brittle. These all terms comes under this effect actually. So once you apply a force in the aim of deforming a solid, then that force is termed as deformation force. Then if there is a change in the structure of the solid or shape of the solid, we'll say it is plastic. Or if you removal of the deforming force, the solid body retain its original form, then we'll call them as elastic. So plastic and elastic, these two terms comes under this effect in the deforming force of effect. So solids mainly we can classify into two terms, elastic and plastic. Some other elastomers also, we'll come to in detail. So what is this elastic and what is plastic nature? Basically, and in elasticity, some detailed ideas we are going to discuss in this chapter. That's the viewpoint of this chapter. So if you apply a deforming force on a solid body, and after removal of this deforming force, if the body retain completely its original shape or form, we'll call as perfect elastic body. In nature there is no such a body, but some materials are there nearly showing elastic nature. So the ability of a body to retain its original shape after removal of deforming force is termed as elasticity. In such a bodies, how much force you applied, the deforming force per area will call as term as stress. So stress is a physical term which has restoring force per area. Pressure also force per area is there. So both stress and pressure have same dimensions. Force by area. Newton per meter square or Pascal is the SI unit of stress. Pascal. Both have same dimensions formula. Stress and pressure. We have stress for different aim, we could say. Mainly longitudinal stress, volumetric stress and tangential stress. For a linear cylindrical material, you apply a force such that its length changes, or aim of the application of force is to change the length. Then that stress restoring force by area is called longitudinal stress there. If you apply the force in order to change the volume of the body, then the stress is called volumetric stress. If the stress created is tangential to the surface of body, perpendicular to the surface of body, then we'll call tangential stress. So these were three concepts we have: longitudinal stress, volumetric stress and tangential stress. Based on these, the effect on the body will be different. So one term, stress, is important in this concept in order to know the elasticity actually. So as much stress is there, if there is a change in the dimensions like length or volume or shape, then we'll introduce a term called a strain. The strain gives you a concept between how much change is there in the configuration with respect to original configuration. For example, there is a 5 cm length of wire is there. You applied a normal stress. That means a perpendicular stress you applied on this one, so that its length increased by 0.01 centimeter. Then we will say there is a change of length. That means there is a strain is produced. That strain is given by longitudinal strain. It is equal to change in length by original length. So longitudinal stress if you apply, there can be a longitudinal strain on the body. Similarly, a volumetric stress is there, then there can be a volumetric strain also. Change in volume to the original volume, the ratio. It gives you the strain, volumetric strain. If your aim is to change the shape of a body, just like this way, suppose a cuboid is there. You apply force tangential to the surface so that there's a shape change like this. Only the upper surface moves, displaces with respect to lower surface. We call there's a shear is produced. This is given by the vertical side it is displaced through an angle theta. This theta is called shear produced. So there is a shape change. In that case, the strain is called shear strain. It is given by the displacement by vertical side x by L. Tan theta you can represent it. That's called shear strain. So we have 3 stresses and 3 strains. The scientist Hooks gave a concept that within elastic limit, stress is always directly proportional to strain. Hooke's law says that the stress is directly proportional to strain, or stress by strain will be a constant. That constant is termed as modulus of elasticity. We have 3 types of elasticity constants. This modulus have crucial role in designing the solid materials. For example, the furnitures we can use metals or wooden furnitures we have. Some are glassy furnitures are there. So each one have its own strength and ability to bear the weight. That depends upon their modulus of elasticities. For example, steel has Young's modulus. Its modulus of elasticity is very high. So that all the cases where we use to lift heavy objects or to bear heavy load, we use steel materials, steel rods we use, steel rope we use it. That is the application side. So what is elastic? Modulus of elasticity. We can go to it. We have 3 mainly modulus of elasticities: Young's modulus, bulk modulus and rigidity modulus. These 3 are corresponding to these 3 stress and strain. Young modulus is longitudinal stress by longitudinal strain. So stress have same unit equation everywhere, force by area. So we can have this F by A into delta L by L. We can write as F into L, the original length, divided by area into change in length. This gives you the Young's modulus. Strain have no unit, so Young modulus also have the units just as that of stress. So stress, pressure and Young modulus, all the 3 have same dimension and same SI unit. Then bulk modulus we have. What we discussed in volume stress and volume strain, their corresponding ratio gives you the bulk modulus. There, in our normal stress if you apply, force by area, we can term it as pressure in the volume cases. So here, P into V by delta V we can write it. And this negative sign shows that as the pressure increases, the volume decreases. This decreasing nature is given by this negative. Yeah, so same unit is pascals, because strain have no unit. Then we have tangential stress and shear strain. These 2 ratios will give you the rigidity modulus G. That's the F by A by theta or F by A theta. These 3 modulus of elasticities we have. Different materials like matter, solid, gas and liquid. These 3 have different ranges of these modulus of elasticities. For solids, we have Young's modulus. Then gases and liquids, they have corresponding modulus of elasticities. We'll come to. Now, based on the Hooke's law, stress is proportional to strain. If you plot a curve, we'll have a stress strain curve like this way. These curves give you an idea about how to compare two materials which have more elastic limit, which have more yield, which have more plastic region, which can bear long, higher weights, which have less breaking point. These all things we can discuss based on this graph, stress strain curve it is known as. So in the exam point of view also it is important. So if 2 or 3 graphs are given of different materials, you have to compare which is suitable for which purpose. For example, a ductile material. A brittle material have less elastic limit, and a ductile material have long plastic region. So things actually in this graph gives given by this. Initially for stress and strain is perfectly proportional. We call A, to the point A, it is elastic limit. After A, it is not perfect elastic, So till B we call the yield point. After that, if you apply without stress itself, strain used to increase after elastic limit. That point after which strain increases, the length of the wire increases without increase in stress. We call as yield point. Then they have plastic region we have, and finally we have the breaking point E, the fracture point. So by comparing the graphs, the area below or this one, we can identify what type of material the second, or like that is brittle or ductile or tough, like that we can identify it. Exam point of view, that you can expect a question also based on that. So stress strain curve gives you a concept of how much it can bear the weight or load, that we can mention it. So here we have 3 modulus of elasticity and one more ratio we can find in terms of lateral strain and longitudinal strain. For a cylindrical wire, at a time if length and diameter changes, both length and diameter changes, then change in diameters we can say as lateral strain, and ratio of this length we can have longitudinal strain. The ratio is there, we call Poisson's ratio. Sigma will note it. So these ratios we have 4: Young's modulus, bulk modulus, rigidity modulus, and Poisson's ratio. I hope you got these concepts. So here for Young's modulus, F by A by delta L by L, you can write as force into original length divided by area into change in length. And for bulk modulus, we have force by area can be written as pressure into volume divided by change in volume. And for rigidity modulus, we have tangential stress by shearing strain. This is F by A is stress divided by shearing strain can be tan theta, and for small angles simply you can write theta itself. That theta will be given by X by L, where X is the linear displacement for the vertical side and L is the vertical side, the length. Theta we have. Then Poisson's ratio we have is ratio minus delta D by D. This delta D by D is the lateral strain, change in diameter to the original diameter. And this negative sign shows that as the length increases, the change in diameter is decreasing, or vice versa. That decreasing nature is given by negative. So lateral longitudinal strain is delta L by L. These ratios we can have. You can link these 3 among also like this way. So please keep in mind also this concept, like Young's modulus Y is equal to 3 into B, the bulk modulus, into 1 minus 2 into sigma. Sigma is the Poisson's ratio. So it is a relation between Young's modulus, bulk modulus, and Poisson's ratio. Another one, Y is equal to 2 into G into 1 plus sigma. Young's modulus, rigidity modulus, and Poisson's ratio. Then 9 by Y is equal to 3 by G plus 1 by B. Young's modulus, rigidity modulus, and bulk modulus. So these 3 give you the different ratios. So based on this ratio, you can link. If 2 are there, the third one you can find out. For that, it will be helpful for you to make use of. And during this stretching, or if you apply a force on a longitudinal wire, because of the stretching, a force or change in length is there, then the work done you can calculate. Work done in stretching a wire, W is equal to half into F into delta L, force into change in length. So for the force, if Young's modulus is given, you can rearrange it. So you can make use of this equation different ways. So it gives an expression for work done in stretching a wire, half into force into delta L. This work is stored as elastic potential energy of the material. That can be written as half into stress into strain square. You can use it. And if on a long beam, if depression is happening on the middle because of a weight, then the depression produced del is equal to WL cube by 48Y into IG. This equation will give you the depression produced at the middle. While doing the numericals, we'll across, so please be thorough with these expressions. So in this topic, we discussed about stress, strain, and Hooke's law. From Hooke's law, we got a constant called modulus of elasticities. We have 3 different and one special ratio, Poisson's ratio. The relation between them also we discussed here. I hope I will give you 3 more equations which will be helpful for you to do application level questions as an application of Young's modulus or modulus of elasticity. See, while designing the rope or a rod, steel rods, to lift a particular weight, how to make it suitable for a particular weight or load. For that purpose, we can design the radius or thickness of the rod or by using this concept. So the thickness of the metallic ropes can be decided by the Young's modulus equation. There you know Y is equal to F into L by pi r square delta L. So there will keep a safety factor of 10. So keep in mind, in a rope, safety factor should be 10. Based on that, we can design the radius of the loop or the wire or the rod, what can be used it. So keep in mind, safety factor will be maximum 10, we keep it. Now, restoring couple per unit twist. If you twist a rod or a wire of length L, then the couple produced C will be equal to pi into G r power 4 by 2L. This G is the rigidity modulus and R is the radius of the wire. L is the length of the wire. So two end of this, one end is fixed, then if you twist the rod, the couple produced, restoring couple will be this much. And for another case, the depression of a beam loaded at the middle. This before I gave the concept, del is equal to WL cube by 48Y into IG. This W is the weight or the load kept at the middle of the beam. Suppose a beam is there. It can be a rectangular as well as circular. And if you hold a weight here at the middle, then it can be depressed. The depression produced is equal to WL cube by 48Y IG, where this IG is moment of inertia because of this twist. So thus IG for circular beam will be equal to pi r power 4 by 4. And for a rectangular beam, IG is equal to B d cube by 12. These equations also you can make use while doing the application level questions. Now, we can check two questions. A question is like this way. A wire of length L and radius R rigidly fixed at one end. On stretching the other end of the wire with a force F, the increase in its length is L. If another wire of same material but of length 2L and radius 2R is stretched with a force 2F, the increase in its length will be. So here we have to make use of this equation Young's modulus. Y is equal to F into L by pi r square into delta L as an expression for material. Young's modulus. Y is equal to force into L by pi r square into delta L. That's case 1. Now for another the same material, another wire it is there. So same material means Young's modulus will be same. So for second material, if you use the same equation, there you are applying a force of 2F and the length is 2L divided by pi into the radius is 2R. So 2R whole square into the delta L dash I am putting the new stretching. So this is the expression for second material. Both have same material, two wires of same material. So Young's modulus is same. So if we equate 1 and 2, you can get F into L by pi r square into delta L is equal to 2F into 2L by pi into 2R whole square. I am writing 4R square into delta L dash. So similar terms you can cancel. FF cancels, LL cancels, pi and pi, R square and R square cancels. 2 into 2 by 4. So 1 by delta L is equal to delta L dash. That means the extension produced will be equal. So here in this question, in the first case extension produced is L. So second one also will be L. B is the answer. So just by comparison method you can solve it. Young's modulus equation you have to keep in mind. Now we'll go to another question. This question says that a heavy uniform rod is hanging vertically from a fixed support. It is stretched by its own weight. The diameter of the rod is. So if a wire is stretched by its own weight, so one end it is connected. So a rod is there. Okay, suppose its length is L. If it is stretching by its own weight, then the elongation produced delta L is given by delta L is equal to, for the numerical purpose, you can make use of this equation also. Delta L will be equal to mgl, the original length, divided by 2ay, where this L is the length of the wire, mg is the weight, m is the mass of this one, so mg is the weight of this wire itself to ay. One equation, please note down it. Now in this question, it says that is stretched on itself, then diameter what will be? Change will be there. So of course, at this end, starting end, the weight will be higher for this, effect will be more here. And at the last end, its weight, remaining weight is very less. So we can say more stretch will be here only. Here the diameter will be very less and here it will be higher. So if this change is there, then it will be at bottom diameter will be higher and the initially diameter will be less. So the options is like this way. A, smallest at the top and gradually increases down the road. B, largest at the top and gradually decreases down the road. C, uniform everywhere, and D, maximum in the middle. So the diameter will be smallest at the top and gradually increases down the road. Here will be smaller and here will be larger. We can check one more question, like identical springs of steel and copper are equally stretched. Young's modulus of steel is greater than Young's modulus of copper. Then, what are the options actually? Less work is done on copper spring. B, less work is done on steel spring. C, equal work is done on both the springs. D, data is incomplete. Young's modulus is given the work done, W is equal to half into F into delta L. So the work done is proportional to delta L, we can say. Now from Young's modulus equation, we can say this delta L is inversely proportional to Young's modulus. So we could say the work done is inversely proportional to Young's modulus. So in these two concepts, this one and this concept, you can make it work done is inversely proportional to Young's modulus. Here is given Young's modulus of steel is greater than Young's modulus of copper. So higher the Young's modulus, less work is required. And lesser the Young's modulus, more work is required. So here the option is less work is done on steel spring. That is option is B. I hope you got this concept. So please be thorough with this idea. Thank you for watching.
Bright Education Center, Medical and Engineering Entrance Coaching Center, Hilal area, Doha, Qatar. For further enquiries, contact 306000679.